All right. So a little bit of a weird week last week. Hopefully that's not replicated throughout the rest of the semester. So a couple things before we dive into stuff today. You had a placement lecturer substitute, whatever you want to call it, last week. My understanding, so I talked with them, I talked with a couple students. So primarily they just went through the theoretical aspect of critical values, confidence intervals, p-values, confidence intervals and hypothesis testing. So they then kind of started on some linear regression stuff. My understanding, you guys just kind of focused on like the theoretical aspect of doing this. So like performing hypothesis tests, building confidence intervals. So today will probably be a lot of Stata work where I'll kind of show you how you would do some of this stuff in Stata. As a result, we go Google Chrome here. It's Microsoft Edge on this computer. So that first problem set, going back here, I've got it so it's set to be due at the end of the day on Thursday. So you should have been able to really do everything in that problem set other than kind of the last couple questions, okay? So I'll show you today, after today's class, you should be able to kind of answer those last couple questions on that problem set. So I think before last week, really we had covered everything except for really how to do these hypothesis tests and kind of make decisions, thinking about the confidence levels, we can reject that. Everything else in terms of looking at conditional means, standardizing variables, that's all stuff that we'd already done. So hopefully you've been working on this because it was already supposed to be due. But because of the kind of last week, me not being here, I've moved it to be the end of the day, Thursday. The only remaining two questions that we should have to cover today would be these last two. So after today's class, it should be, and hopefully we'll see this is going to be relatively, hopefully quick and easy thing to answer these questions based off what we talk about today. Okay. So got that. I've got some people, that quiz was supposed to be due. When I'm not in class, the best I can do is not email every single one of you, but use Canvas to put out announcements. It's essentially me emailing all of you. So pay attention to Canvas announcements. It's the way I communicate with you outside of class. Anything that I need to tell you that I'm not able to tell you in class and between classes, that's where I'm going to do it. Okay. So I understand though, it's a little bit of a hiccup after today's class. In fact, I'll switch this right now out of fairness. You want to complete that by the time we start class. Next class, if you miss that, it'll kind of give you an opportunity to kind of get on, make sure you're getting that done before we start class on Thursday. Okay. So then we should be kind of all caught up. I'll have this in-class quiz. We might take a look at this today if we get far enough into material. But other than that, we shouldn't have anything missed other than that problem set, which once again, so that's under the assignments. You can see this all from the homepage. That I've already got that due date set. Where's that? To be the end of the day, Thursday. Right. So once again, we should have covered everything you would need after today's class to answer that, but give you a couple days to kind of make sure you get on, complete that problem set. And I'll mention a little bit more about kind of your uploads and what those should look like. If you've already uploaded it and completed it based off of, probably Google search and kind of figure some of it out. I'll mention if you've already uploaded, it's probably okay, but kind of moving forward, what these submissions will start to look a little bit more like, okay? So with that being said, we will kind of start thinking about some of this hypothesis testing and confidence interval stuff today. And I will probably transition into this week's material, which will primarily be linear regression. So talk with how far into linear regression did you guys get? Just kind of the basic setup. I don't know. Did he show you any like regression output, or were you primarily just talking about kind of the theoretical, like where these coefficients come from? Not sure. Like, did you see any output? No? Okay. So that's what I thought he got through. So he didn't see anything that looked like this. Okay. That's right. Okay. Then we're all on the same page. And I'll probably go through this relatively quickly, some of these early slides, but we're not there yet today. We're going to go back a little bit. Okay. So when we're talking about doing things like hypothesis testing, what we're doing is generally we have like different types of tests. Once we get to linear regression, we're really only going to be talking about one of these types of hypothesis tests, right? So I said you could have this setup where if I had, let's say, I'm looking at, and I think I was writing it as Y, you could write it as X. If I'm looking at the sample mean, if I take a bunch of different samples, and I kind of showed you this, not last week, but the week prior, that Thursday class, I was saying like, I was using Stata to like randomly sample like 1,000 different times and then graphing out those sample means. We said they would always kind of be distributed normally around what? So if I had the population data and I just kept sampling from it, all those sample means should be centered around whatever the true population mean was. Now, we often don't have the population data, and all we have is one sample, right? I mean, you have one data set, right? It's not like you can do this theoretical thing where you keep resampling the data. Usually we just have one sample data set. So what we're going to do is say, well, look, we don't know this mean, but we're going to say, let's assume that that mean is equal to some specific value, 50, 29.5, depends on the variable we're looking at. We think that the true mean is some value. We call that the hypothesized true mean. Well, if that was in fact the true mean, what should my sample means be centered around? That value. So we're going to assume that that's the true value, the true population mean. We only ever get to see one sample. So this would be like the sample mean value that we found. Well, we know that if we just take random samples, even if this was in fact the true mean, that a certain percent of the time, we're going to see, right, there's a likelihood that we see something, let's see if I can remember these ones off the top of my head. So this would be, if I were to go 1.96 standard deviations above and below that true population mean, there's only a 95% chance I see a sample mean somewhere in that range. So even if what I'm assuming to be true is in fact true, 95% of the time, I'm going to see something that's approximately 2 standard deviations above and below. But 5% of the time, I'm still going to see values that are out here. Okay. Now, I have to basically set a confidence level where I say, look, even though it's 5% likely I could see a sample mean out this way, that's a pretty low percentage. So I'm only okay saying that this is in fact the true mean if I see a value that's somewhere within 2 standard deviations of that assumed true value. If I see something outside that range, there was less than a 5% chance I saw any value in that range, let alone one of these values. So if I see anything outside of this range, this probably isn't the true mean. It's probably, if I see the sample mean way out here, it's probably more likely that the true distribution is somewhere over here, right? Making this value a lot more likely for me to see. So what we're doing with hypothesis testing is we're saying, okay, look, I'm assuming that the true mean is equal to this value, but if I see sample evidence that goes against that being the true value, if it's so unlikely for me to see this value, if this was in fact the true population mean, then I'm going to reject this. It probably isn't the true mean. It's probably that the true mean call this the probably true mean because it doesn't really have a name. It's probably somewhere out here, right? So we're going to kind of set these bounds based off of the fact that we know that this is our sample means will be normally distributed based off of a student t distribution. Okay. Now we said we have a set of student t distributions, but if we can get large enough sample sizes, what's happening to that distribution? So just to kind of review, we said when we looked at this set of student t distributions, and I was looking at the sample mean, and this is where I took a bunch of different size samples. So let's say I took samples of size 30. If I instead took samples of size 15, what's going to be true about the distribution of those sample means? Well, if I've got smaller samples, what values are going to be more likely for me to see when I look at the average? If I'm looking at like average height, If I've got 2 people, maybe I see an average height of like 6'5" and just happen to get 2 really tall people. But if I've got 50 people, what's the likelihood the average height across 50 people is 6'5"? Almost improbable, right? And so as I have larger samples, what are my sample means going to be closer or more tightly distributed around? Whatever that true mean is. So as I take larger samples, we can think about, so if I took samples of size 100, what's going to happen to this distribution? Values further from the mean are going to be less likely for me to see. Values really close to the mean are going to be way more likely for me to see. So my distribution gets more and more peaked as I have higher and higher samples. And in fact, as I have higher and higher samples, what is my student t distribution getting closer and closer to? My standard normal. So in general, we say if we can get a sample size over 30, our student t is approximately already a standard normal. It's not quite, right? But it's close enough to where we can use those standard normal values to approximate them, which is how I knew 1.96 was the value, right? So we don't have to like always go to those student t tables. We can really just use the standard normal values and they'll start popping up a lot. Now, I set this up in terms of kind of like a two-tailed test where evidence on either side would go against this being the true population mean. Last week probably talked about right versus left-tailed tests. Sometimes we're only, we assume that it's this value or something less. Well, there, the only evidence that would go against that is if we find values that are really high. For linear regression, which is basically what we're going to do for not just linear regression, we're going to do regression analysis for the remainder of the class. What we'll always be looking at, is not sample means, but we're going to be looking at the distribution of something called our sample coefficient, okay? Now, what we're always going to do with linear regression is we always start out assuming it's nice and easy. We don't have to actually worry about right, left tail tests. We're going to assume the true coefficient is equal to 0. And we just want to see, can we find evidence from our sample data that goes against that? So we don't care if we see positive or negative values. We just care, is it anything different from that assumed true value of 0? So we're always going to have two-tailed tests. We're always going to be able to come up with a lower bound and an upper bound where we can say, if the true coefficient is 0, 90, 95, 99% of the time, it's going to be within this range. And then 1, 5, 10% of the time, those are generally the benchmarks we use, 90, 95, 99%. 100 minus that percent of the time, we'll see something outside of that range. If we see something outside of that range, it's probably what we assume to be true, probably isn't in fact true, and we're okay rejecting it. So we're going to come up with these upper and lower bounds. These are essentially, do you remember what he called these maybe? Starts with a C. They're similar to confidence intervals. We can build those, but the actual bounds where we say, if I see a test statistic greater than or less than this, we would call those critical values. If I see any test statistic, so I take my sample mean or my sample coefficient and I turn it into a test statistic, if it's any larger than my critical values in absolute terms, then I'm okay rejecting what I assume to be true. So I'll kind of build some of these out as we look at this in Stata. I'm just trying to kind of give us a little bit of a refresher maybe of what he should have hopefully had covered and the thing that we'll kind of be talking about today. Okay, so just looking somewhat familiar. Okay, seeing some head nods. So what we're going to start out with, and we'll do a little bit of a Stata refresher here as well. So I've had a lot of people reach out, even last week, and I think I met with someone Friday, kind of making sure we can all have Stata working. We can open up data sets. If you can't at this point, you're behind the 8 ball. As I've been trying to kind of nudge you kindly, you need to reach out to me if you're having problems with this, right? And so what we're going to do today, I've got the program open, right? So I just went to, there we go. I went to IU Anywhere. I opened up Stata. This is just the program. Now, I was showing someone some stuff for class. I'll clear this out. just so that we don't have anything. It's almost like I just opened it up. Oh, sorry. Now you guys can see it. So I went to it. I can go anywhere, open up Stata. I've got the program open. I was showing people some stuff before class, but let's assume that I just open it up. It would pop up with this box that just looks like a program. Okay. I can't save any of this. Okay. This is just showing me what the program is doing. I said you should have 3 windows open when you're working on Stata. One, the program. The second would be the data. Well, if I go to this data editor, the browser with a magnifying glass, it's blank right now. This is the second window I should have open, but I haven't opened up a data set yet, right? So it's nothing there, okay? The third thing I need is my do file. Now I can click on this do file editor and open up my do file from here. What I can also do is if I go to file open, and here I've got mine in certain folders. So we're gonna wanna look at week 3. I believe the do file I have is this confidence, is this what I want? Yeah, we can do a confidence interval example. Click on that. So this is kind of where I'll run through another example talking about confidence intervals and hypothesis testing. So I've opened up the do file from the program. It'll open it up in this do file editor for me. Hasn't done anything though. Hasn't opened up any data. It's just showing me all of the code that I'm going to eventually run. Now, where does this come from? I'm giving this to you on your problem sets. You're typing all of this out, right? This is really what you're going to want to upload for that problem set. This is all of your work. Okay. So now what's a really good thing to do? I mean, because we'll use this later on, I'll open up another do file here. Back a little bit earlier this week. Well, nope. It was in week 1 and 2. That review of statistics, I would have this pulled open as I'm working on my do file for my problem set, right? I kind of mentioned this before. Anything that's probably in here, there's, probably you could use, there's probably some question somewhat related to it that you need to use for your problem set. So we're going to scroll down here because we left off thinking more about, where is it at? We didn't get to the stuff that I had under week 2, right? I was going to do this in week 3. In fact, I could even change this. This is stuff that kind of went along with week 3 material, right? Now, I said this global path, it's always going to change. So I think I have it correctly stated here. If I, for some reason, this is, obviously yours is going to look a little bit different than mine. So I said one way to kind of set this global path so you can work along with me in class is to go back to the actual program, wherever you've downloaded that MBA height data. So this is where I want to open the actual data set. So whatever folder you have it in, when you open it up from there, so I'm going to just open up that MBA height data. Actually, now that I say that, am I using the MBA height data? Nope, I'm using the election data. So it doesn't matter. I can make the point here, right? Even better. So I just opened up the wrong data set, but they're all in the same place. So the first part of this up to, I don't care about the file. I just want to know where is it at? What's the path? So I'm going to copy this. So Control C, right? I'm then going to go back over to my do file. And I now know, okay, even if this was the wrong one or wherever you've put it on your file, once you open it up once, you know where that file path is. You know where the data exists. And I've told a lot of people, I were you, I wouldn't break this down week by week because it'll be easier if you just throw all the data files for this class in one folder called ECON 371. Guess what your file path will always be? The exact same thing, right? So just throw all the data sets into that same folder. That way, every single time you're working on a do file that I give you, you can just always have that same file path. Now I'm being annoying because I'm putting them in different files, so I have to constantly update them, but that's no sweat off your back, right? If you just throw them in the same folder, you can always use the same file path here. You'll just have to change my do files to be whatever my file path is to whatever yours is, okay? Is that, yeah.
Somewhat different, but for the election data, how do we switch it from Excel to the .dta again?
Yeah, so I've got the path here, right?
Oh, is that through there?
I'll answer your question. Sorry, I'm not trying to shut you down, but so I've got my path now. I could do this one of 2 ways. Since I'm giving you this code, as long as you've downloaded that election data and you have it in that folder, the same folder as you had the NBA data and all the other data sets, now hopefully when I set that path, I've got to come here. Notice I'm not using data. So if I were to just try to do this manually, and I go to File, Open, I can open up like that NBA data set, but notice it doesn't give me the election data as an option. Because all the program can do is open up Stata data files, .dta files. So I can open up .dta files, and I'll try to give you these as .dtas as much as I can. Some of the data sets I have just happen to be in a different form, and it's good that you get practice like converting these data sets. So if I wanted to instead open that election data, I could go to File. Well, I can't open it. It's not a .dta file, but I can import all these other types of files. So like if you have other classes, there should be an SPSS, there's CSV, you can even, it doesn't have an option here. There's a way to take files that are in R to kind of convert them. You can import, I think it's an Excel file. See if I'm right. Oh yeah, now it's showing me that election data because it has to be, you can, if it's importing it, it's a different type of data set. Excuse me, I've selected Excel, now it can identify that. If instead of doing that, try to make it easier, if we can get this file path kind of to be like second nature. Well, now notice I've got a different line of code. It's like import. It's not using because it has to import this data. But if you get the file path set correct, it'll import that election data file, and now it's converted it into a .dta file. And if I really wanted to, I could also go to like File, Save As. Now when I'm saving it, it'll save it as a .dta file. There's no reason to necessarily do that. It's just going to take up more space on your iDrive, but we could if we wanted to, right? If you don't like to keep importing it, now I can just open it up as a data file once I save it as a .dta. Does that answer your question? Okay. Any other questions up to this point? Okay. So I've got this file opened up and I'm thinking about, I've got this election data. So I don't know, I've got some things here. I like to rename variables sometimes if they're really long, just to make it easier when I'm typing things out. You could do this if you wanted to, you don't have to. Let's just run this line of code. I'm going to rename this percentage 20 Donald Trump to Trump 2020. So this is just the percent of the votes that Trump got. Now, if I look at the data, sure enough, it's renamed that variable to be a little bit shorter, a little bit easier for me to type out. Now, if I try to rename that variable again, well, it no longer has the same name. It's going to give me an error, right? So you only have to rename these variables one time. And then from there, you just have to call it whatever you've renamed it to, right? I've renamed it to be 2020. Okay. And then I can do the same thing for the Biden variable. So if I select code and I just go up this little play button, it runs that line of code. Now I go to look at the data. Okay, it's renamed that variable to be a little bit shorter as well. Any questions? Not before I keep moving. I think I showed you how to rename variables before, but just kind of want to be complete here. So I can look at the distribution of different variables. We already talked about this. This is just using that hist command. It'll draw a nice little graph. Takes a little bit of time. It's thinking. There we go. So I can kind of look, okay, the unemployment variable across these different, I think it's counties. I don't think it's cities. Okay, it's pretty normally distributed. Maybe has like a little bit longer of a right tail than a left tail, but pretty close to a normal distribution, right? So I was then thinking about, all right, I want to know, is there maybe a difference in the percent or the proportion of these counties that were voting for Trump based off of, do they have high or low unemployment? That seems like a reasonable question, right? So what I'm going to do is first create this variable that I'm going to call the mean of the unemployment variable, right? All it's going to do is create this new variable. And I had someone the other day meet with me and I said, well, what's the difference between eGen and Gen? So does anybody remember what's the difference between eGen and Gen? Gen does.
It's a new variable.
They both create new variables, but Gen will just do basic math, right? So for example, I've taken like Gen here and I said, create this new variable if this is true. So if this is greater than this, eGen is going to use built-in functions. So for example, if I want to calculate a variable and I want it to be equal to the mean, Well, how do you find a mean? You actually have to go through the data. If you were doing this by hand, what would you do? Add up every single value and then divide by the number of values. I didn't type that out there. I just typed out a word. So it basically has this function stored behind the scenes that calculates the mean like you would by hand. So anytime I want to use a function that does something that I would have to do by hand that would take a lot of time, it's built in. That's ECON. It's essentially telling Stata, all right, there's all these pre-programmed words. I want to use them. They tell you to do a certain mathematical function. In this case, to create a mean. So ECON will say, take the mean of this unemployment variable, create a new variable that just gives me whatever that mean is. Now, that's not a very interesting variable, right? Because what will that do? It creates a variable, but it's the same for every observation. Right? It's just the mean of the unemployment across my entire data set. But it might be useful in creating some other variables here, okay? So the second thing I'm going to do is say, well, I want to create this variable that tells me it's a 1 if it's a high unemployment rate county or a 0 if it's not. Well, if it's a high unemployment rate county, the way I'm going to identify these is that county's unemployment above the mean? If it is, so anytime I kind of have this gen command and I'm creating this new variable, high unemployment, whatever conditional statement I put in parentheses, it's going to say, if this is true, put a 1 in for this new variable. If it's not true, put a 0. The only two values it'll do. So it's going to create what we are going to end up calling indicator variables, right? Or sometimes I'll call them this. I guess there's like a movement. It's all good and well, but we're talking about data. I don't like to I call them dummy variables. Apparently that's like a slight now, you're not supposed to use it and it's not PC. I accidentally use it all the time because that's how I learned them, right? But a dummy or an indicator variable is a 1 if this statement is true, a 0 if not, okay? So if I create this variable every time, so I'm going to create this new variable, every time unemployment is below the mean, it's going to put a 0. Every time the unemployment of a county is above the mean, it puts a 1. So we're going to do this a lot once we get to regression because indicator, dummy, categorical variables are going to be something we use a lot of. Okay. So create this new variable, 1 if this statement is true, 0 if not. I could then take a look at it if I really wanted to. So I think I use tab or sum. You can use either one. It kind of gives you, okay, the mean is about 0.45. Looks like there's a few more counties that have below the average than there are that have above the average. So it's not a perfectly normally distributed variable, but it's fairly close. It's not exactly a 50-50 split, but it's near that, right? So I'm then going to use this variable. I could do the same thing, but I could create a low unemployment rate variable. And all I'm going to do there is change the direction of that sign. Now, what should this do? Every time unemployment is below the mean, that statement will be true. So now for this new variable, every time they have low unemployment or below the mean, it'll be a 1. Every time it's above it, it'll be a 0. So it should be the exact same variable I just created, but the inverse, right? So if I go ahead and I run this, and then I look at the data, notice every time I've got a 0, I've got a 1 over here, because that's just the exact opposite statement, right? So I didn't really create a whole lot of new information here, but I'm just trying to kind of give you some more examples of things. You can also, if you create these indicator variables, we can start to look at what we would call like conditional distributions, where I think maybe like in question 7, there was a little bit of this. We might want to look at conditional means. Now, what I'd already told you ahead prior to like confidence intervals and hypothesis testing, you probably could have reasoned your way through this. But like, let's say I wanted to know what the distribution of the unemployment rate variable looked like if it was a high unemployment rate county. So this will only graph out the distribution of unemployment for all of those counties that have high unemployment. So I can go ahead, any command that I've been using before, so hist, sum, all these other things, I can look at conditional like distributions. I can look at conditional means. I can look at conditional variances if I really wanted to. And we'll kind of notice, if I look at high unemployment, the only high unemployment rate county, it was a high unemployment, it had above the average. So it starts at like what, 6 or whatever it was, 6.3%, and then kind of goes from there. So this isn't really providing me with a lot of useful information, but it will give me kind of both sides of the distribution essentially. I just wanted to kind of use this to show you, you can use these conditional statements to like only look at the distribution of this one category, right? Excuse me. I could also say, use this by sort command. Now this will be a little bit more useful. And once again, in these do files, I always try to give you the text of like what it's doing. And so when you're working on these problem sets, instead of you like telling me what it's doing, usually what are you going to tell me? The answer to the problem, right? So it's pretty easy if you do your code in the do file and then right next to it, use this comment, this double backslash to then tell me this is the answer based off of the code. Because a lot of the time the code's not going to tell me the answer. A lot of time it's going to give me some output or even like a table, and then you have to find the statistic that you want or whatever the question I asked you, you know, wherever it is in the output. So you might have to report to me that you know how to find that value given that line of code.
So when you're grading our thing, will you only be looking at those comments then to like grade for accurateness?
I mean, I'll look for partial credit. I'll look at, if you don't get it right, I'll look, you know, probably get partial credit if you use the correct command, but you got the wrong value from the output. So I will be looking technically at both. You know, if you have the right answer and I see the code there, you need both of those pieces of information. If you just have no code, but you have the right answer, what do I probably think you did? Work with somebody else, you know, like, so you need to have the code and then also the answer to kind of get the complete points. Yep. And it also allows you to get partial credit as well. Yep. Now, if you've already done this and all the answers, you have like your do file of code and then you put like in a Word document, the answers from that, that's okay. It's a little bit harder for me to grade. You might not get, you know, I might not get through them quite as quick. It's easier for me if you get used to like putting it all in the do file, just because I've got the code and the answer right there. But if you've already done it in a Word document, you can always upload your do file and a Word document. It allows you, to upload multiple files, and that's okay if you've already done the work that way. Okay. And some of these you will have to, especially this first one, probably moving forward, not so much. But like if I ask you for the scatter plot, you can't copy and paste the scatter plot in here. So you might, copy and paste. It's a visual. You might have to copy and paste this into a Word document. After this first assignment, there really won't be much of that. It'll primarily be you've got some code. It's going to give you some output. You then have to find whatever the statistic is or answer the question based off of that output. Any questions? Yeah.
Did you say you want our answer given as like backslash and then our answer?
Well, if I don't do this, right? I mean, technically that's okay. But if I try to run your do file, it'll give me an error here. What helps me out is, so I'll show you. If I were to open up one of these do files, as long as I have the path set right, we'll see if this one works. No, because I don't have the path set up right. So let me see. I'm not going to save this, so it doesn't matter. So let's say I had this do file. Oh, that's because I showed you something that doesn't work. But if I just don't select anything and I hit the play button, it'll run the whole do file. So if you upload the do file and you use these comments, it'll run your whole do file for me. I can see all of your commands are working correctly. And then I can just look at your comments. It'll pop them up like right here. And I can see, oh yeah, you gave me the correct response. If you don't, I can look at the do file. It's not the end of the world. If you don't put these double backslashes, it's just that if you don't put them, file can't run, because then every time I don't have a double backslash, so if I tried to run this whole do file, it's going to give me an error because it doesn't know what the hell look at distribution of variable means. Or it doesn't know how to identify that text. And so that's why if we just wanted to skip over something, treat it as text and not a command, that's where we use that double backslash.
Okay.
Does that make sense?
Yeah.
So do we have to create the global class, like the global path of before we turn in our do file?
No. This is the global path is more so for you to work along with me in class. When you're creating your do files for your problem sets, you can just have the file open command at the very top. You don't have to like set the path every time for that. No. Does that what you were asking? Yeah. For the problem sets, I don't. If it's trickier to use those file paths, don't worry about it. It's just those file paths are a way that you can use the do files where you're doing a class and kind of work along with me. Okay. Any other questions? We'll keep moving. Okay. All right, so now I've got to make sure I open this back up. Rename everything. Where did we leave off? We were down here. So I had this by sort command. So another thing that we might use a little bit, or you might see me use, is this by sort command. So this will basically look at all the possible values for this low unemployment rate variable, and it'll summarize a variable for me. So what this is going to do is it says, look, I've got this low unemployment rate variable. I know that it's a 1. The county has low unemployment, 0 if it's. I then want to summarize the variable, but for the different values of this. So what it's going to do is for every county that has low unemployment, it'll calculate the mean, summarize. It actually does more than the mean, right? It calculates the mean, the standard deviation, et cetera, but just for the counties where low unemployment is equal to 1. It will also do the same thing, but only when that low unemployment rate county is variable is equal to 0. So I go ahead and do this. What I'm now getting are conditional means. So it says, look, for all the low unemployment rate counties, when it's equal to 1, the mean of this Trump 2020 variable is 0.67. When low unemployment is equal to 0, so that means it's a high unemployment rate county, the proportion that voted for Trump was 0.63. So what is this really telling me? What counties are more likely in this data set to be voting for Trump? Which one has a higher mean? 0.67 higher than 0.63? Yes. So low unemployment rate counties were more likely to have a higher percent of their population vote for Trump. I mean, probably what you might expect, right? If you look at the data, lower income, lower socioeconomic counties tend to vote a little bit more for the Republican candidate. Okay. So we can look at conditional means, right? And that starts to tell us something about the data. Now you can also create new variables. So you don't just have to summarize things. You can use this by sort command also to create new variables. So what this will do is it's going to find the mean of these low and unemployment rate counties. So it's going to find these same two values, but it's going to create a new variable where it puts the mean for the low unemployment rate counties in, if it was a low unemployment rate county, and it's going to put the high unemployment rate mean in for all the high unemployment rate counties. So if I go ahead and run this and then take a look at the data, what I'll see is what it did is it went through, and every time there was a high unemployment rate county, it put in the high unemployment rate county mean proportion of votes for Trump. We'll have to scroll down because it sorts the data. Every time it was a low unemployment rate county, okay, now it puts in the mean proportion for the low unemployment rate counties that voted for Trump. But now I have an actual variable. When I use that sum command, it's just visual data. This isn't stored anywhere. So this is helpful if I'm like just interested in the value, but if I want to use that value later on, it's not saved anywhere. If I'm creating new variables, I can then potentially use that later on because it's now stored here in this new variable. So it kind of just depends on what I'm wanting to do, right? So I've got different things here. I think I created a high portion of white individuals living in a county. So it's the same thing that we were talking about, indicator dummy variable, just if the white proportion, I think it was actually not proportion here, if I'm greater than 80, that must be percentages, right? So if the percent of the population that was white was above 80%, I consider that a high white population county, 0 if not. I did a high income county, creating this variable. So this is where, working along with me in class, we can kind of just run all this code. So initially I did kind of the high white, so we'll do this. I then kind of summarized it by that. Not that surprising. High white proportion or population counties had a much higher proportion vote for Trump than the non kind of high white proportion county or population counties. I then did a high income. You can also start to do multiple conditions, right? So I created this dummy variable, which was, did it have income above 75,000 on average? It's a pretty wealthy county, right? So I then said, okay, I don't want to just make one conditional statement true. I'm gonna say if the income high I created, if it's not equal to 1, so that's telling me these are gonna be what? Lower income counties, right? Counties that if this variable is equal to 0, that means their income wasn't greater than 75, it must have been less than or equal to. Or if the county has a high proportion white. So these are gonna be high proportion white counties that are lower income. These are gonna be my rural counties, I'm guessing West Virginia, right? Like some of these like more rural southern counties. So if I create this new dummy variable, it's only equal to 1 if either of these are true. So I think I did a little bit of this before, but just to refresh our memory, if I want to see if 2 things are true, I can say if this is true, or, so this vertical line is or, and is just the and sign. Right? That one's kind of easy. So here I said if the high income variable is not is it equal to 1 if it's not equal to 1. So there isn't like a symbol we can type on the keyboard that's not equal to. So the way that we identify not equal here is a exclamation point equal. That means not equal to. So if this variable is not equal to 1, or this variable is equal to 1, then I'm creating this new indicator or dummy variable, which is a 1 if if either of those statements are true, 0 if not. Okay. So, and then I can kind of look at, what does that look like? Once again, not overly surprising. If I'm looking at high income, high proportion kind of white counties, they tend to have a higher proportion vote for Trump than if neither of those are true. All right, so any questions over anything for now? Building this up, we're finally getting into kind of this hypothesis testing stuff. Questions before we keep moving? Okay. So I might have this idea, is the proportion of votes for Trump in 2020, did it vary across counties that were high and low unemployment? So we can start to test for differences between 2 different groups. So what we're really doing when we do this is we are saying, we're not interested in a mean, right? We're actually interested in the difference in means. So what we're going to do is say, look, our hypothesis test is that the difference between group 1 and group 2, now we can simplify this here in a second, but now, is that difference between the 2 groups, we're going to assume it's equal to 0, which is really saying what? That their difference is 0, that means there is no difference, right? They're equal. They're equal. Or another way we'll think about this, we're saying that the difference between these 2 groups is equal to 0. Now, when we take a sample, what are we going to see? We're going to see not the true difference, we're going to see the sample difference. Or, we could write this in, for thinking about like a mean, sample difference, just slightly different notation. Once we get to linear regression, we're going to be using it's generally a hat. Either one of these is really saying the same thing. It's kind of the sample difference that we're finding from the data. Now, if what we assume to be true, if this is, it's a hypothesis test, so we don't know the true difference, we're assuming it's equal to 0. Our sample difference should be, as long as we have a sample size over 30, normally distributed around whatever that assumed true difference is. So we're then saying, okay, we can start to build confidence intervals, or we can start to look at different levels of confidence, where we say, if I see anything 1.96 standard deviations above or below that assumed true difference, then I'm okay accepting that as the true value. I'm okay saying that there is no difference. But if I, from my sample evidence, from my sample data, see a difference that's anything more than 1.96 standard deviations away from that assumed true difference of 0, I have found sample evidence that's strong enough that goes against my assumption that my assumption is probably not right, and I should reject that null hypothesis. So how do I know, how do I know if it's out here, if it's in here? That's where we're going to create a test statistic, right? And our test statistic, if we're doing a mean, it would be take the mean, subtract the assumed true mean, divide by the standard deviation of that sample mean. The same is going to be true for every statistic we look at. When we create a test statistic, if I'm not looking at the mean, but I'm looking at the mean difference, I'll subtract that from the assumed true value of that statistic, so the assumed true difference, and then I would have to divide that by the standard deviation of that sample statistic. Now, this gets a little bit harder to calculate. We won't dive too deep into it, but if I'm looking at two groups, I actually have to take the variance of both group, add them up, take the square root. Stata will do all that work behind the scenes for us. But the general way we calculate a test statistic, take the sample statistic, so sample statistic, subtract the assumed true statistic, divide by the standard deviation of that sample statistic. So when we're looking at linear regression, we're going to have a very similar thing. Remember earlier in class, I said we're going to assume that that coefficient is always equal to 0. We always have a two-tailed test. My test statistic is always going to be, well, what coefficient did I find from my sample data? I subtract the assumed true coefficient, which for us is always 0. So it makes calculating it a little bit easier. And then we're always going to divide by the standard deviation of that sample statistic we're looking at. We have a fancy word for this when we get to linear regression, which is this is our standard error. We're never actually going to be calculating this by hand. This is going to be something that Stata is going to calculate for us. Okay? And I'll probably next class, at least, or even towards the end of today's class, show you what that equation is, but we're never going to actually have to calculate it by hand. Any questions? This is hopefully starting maybe a little bit more bigger picture, kind of tying all these different concepts together. So leave this up here a second. I'll switch it over pretty quickly. So if I want to run this test, or is there a difference between two groups' means? That was my kind of example I set up here. I was looking at the average difference between these two groups. Right? So what I'm going to do is I can use this t-test command. Okay? And I'm going to say, look at this variable, which is the proportion of votes for Trump in 2020. What two groups do I want to compare? I want to compare I have to use a dummy variable here when I say by this variable. So this variable, it has to be a 1-0 variable. That's what we were creating earlier. 1 if it's a low unemployment rate county, 0 if not. Excuse me. So by those two groups, test to see whether or not there's a difference in this Trump 2020 variable. And then this unequal, for the sake of this class, we're always going to use this command of unequal. If you put equal, you're assuming the variances are equal. This is, I don't know, not the focus of this class. It's like more experiment, like hard sciences, like physical sciences, where they know these two populations have an equal variance. They've just taken different samples. For us, most of the time, we have no idea what the variances are, so we should not assume they're equal, right? If this was like a more experimental, like lab setting where we know maybe that these variances are equal and we just have two different samples, then we might say we're going to assume the variances are equal. But for anything we're going to do with any data sets you would look at that aren't from like a physics lab or a biology lab, you're always going to have an unequal variances, okay, between the two groups. So I go ahead, I can run this, and it gives me all this output. So it's kind of nice. It tells me, first of all, what are the means of these two groups? Now, we'd already looked at that ahead of time, and we could kind of visually see that, oh, the low unemployment rate counties had a higher proportion vote for Trump. So it at least looks like there is a difference. But remember, even if the difference was 0, there's still a distribution around that. We could see, from any one sample, a positive difference between those two groups or even a negative difference, right? And we want to know if it's far enough away from 0, then we're okay rejecting 0 as the assumed true value. So the part that we really are interested in is, okay, here's our sample difference. So this would be like our D bar that I was writing. It's just the sample difference between these two. It's got kind of some standard deviations and standard errors calculated. That was kind of what was being used to calculate that standard deviation of the differences. It does all that for us. It then spits out at us this test statistic. So T equals, that's our test statistic. And say, okay, you could have a right-tailed test, a left-tailed test, but really anything we're gonna do for this class, we just wanna know, is there a difference, right? And so we're gonna look at that two-tailed test. And what it says is the p-value associated with this test is essentially 0. So I was setting up these to think about. I said, like, if the test statistic, there we go, is greater than 1.96, these were what we were going to call our critical values, okay? So you can do a hypothesis 2 different ways. So one way is I could say, look, I know that if I go 1.96 standard deviations, if I'm looking at kind of a Z value here, or technically, because we don't have an infinite population, student T value, that the probability I see something within 1.96 standard deviations above and below is 95%. Okay? So I was then going to calculate my test statistic and say, if it's anything above 1.96 or below negative 1.96, I'm in what we would call our rejection region. Okay? So these values come directly from that standard normal table. Right? We set the confidence we want. So usually that's 90, 95, 99%. Here I'm using 95%. That means that the values I'm using that would give me 95% in between these two, or a probability of 0.95, that I see a test statistic if what I assume to be true is in fact true, which is that that difference is 0. 95% of the time I'll see a value in this range. So if I see a test statistic that's any further than 1.96 standard deviations away, I know that my sample evidence was inconsistent with these two things, or the difference being 0, or these two means being exactly the same. And I'm okay rejecting that they're the same. The flip side of that is saying, well, if I found a test statistic that's out here, how do I find the p-value? So the way that we think about the p-value, it's the probability, if what we assume to be true was in fact true, it's the probability we saw the test statistic we did, or anything more extreme, right? Now, problem is, we're only ever going to have one test statistic because we had one sample. But if I don't care what side it's on, if I have a two-tailed test, seeing a test statistic here, it would have been equally as likely for me to see a test statistic that was, the gap was that large, but on the other side. So our p-value would always be kind of the area that's more extreme than our test statistic multiplied by 2, right? Because if we don't carry either side, we're always going to have two sides of this distribution. We can find the area of 1. We know, though, it was equally as likely we found evidence on the other side, so we'd multiply it by 2 to get our total p-value. Now, what's nice with Stata is it reports to us that p-value, it's already multiplied that area by 2. My p-value here is essentially 0. So what is a p-value of 0 telling me? Well, it's telling me, how would I get a p-value of 0 from a test statistic? It would have to be that the test statistic is really, really large. So the larger my test statistic, what's happening to my p-value? It's getting smaller, right? So really large test statistics, you can kind of think about, what are we trying to look for when we reject? We do it 2 ways. We reject if the absolute value of our test statistic, because we're just concerned about magnitude. And if we're negative, then everything we have to start thinking about larger negative values are actually less than, but it's a larger in magnitude. If that test statistic in absolute value is larger than our critical value, what that's also going to imply is we should reject, and it will result in our p-value is going to be getting really, really small, and it'll end up being less than alpha. So what is alpha? When we start to think about alpha, the fact that there was a 95% chance that we were 1.96 standard deviations above and below, alpha is going to be the area that would be in our tails, or the probability I saw something that was further than 1.96 standard deviations above and below. So here, if I know that there's 95% in between these, or 0.95, What's the probability I see something outside of that range? In our example, our alpha would have been 0.05. So if we ever see a p-value here that's less than 0.05, or a test statistic that's greater in absolute value than 1.96, both of those will lead us to reject. And that they will both always have to be true. If your test statistic is greater than 1.96, so if my test statistic is greater than 1.96, what does my p-value have to be less than? 0.5, right? Because if it was 1.96, what's the total area in my tails here? 0.05. So as soon as that test statistic is a little bit larger, I now must have an area that's a little bit smaller than 0.05. Now, what's nice about using the p-value approach is we don't have to go out and look up the critical values every single time. Our benchmark values when we're looking at these hypothesis tests are always going to be the 90, 95, 99% confidence levels. So if I've got 90, 95, 90% confidence in this range, well, what percent would be outside of that range if I'm looking at the 90% confidence? 10. Alpha is always in terms of proportions or the decimal form. So at the 90% confidence level, my alpha is going to be what? 0.1, 95%, 0.05, 99%, 0.01. Well, now when I have one p-value, let's say I had a p-value of 0.04. What levels can I reject at? Well, I only reject if that p-value is less than alpha. So what levels can I reject at? Is it going to be less than 0.1? We can't make this comparison. It's going to be a long semester. 0.04 less than 0.1? Yes. So I can reject with 90% confidence. Is it less than 0.05? Yes. So I can reject with 95% confidence. Is it less than 0.01? No. So I would fail to reject with 99. I couldn't with 99% confidence say that there's actually a difference between these two. Okay. Is that making sense? Questions on that? Now, I'll try to come up with some interesting ones as we progress throughout the semester. This is not that interesting because what's the p-value? Okay, so what levels can I reject at? Whatever the hell I want, right? The p-value is going to be less than any alpha if it's basically 0. So what this is really telling me is I have a strong result here that the difference between the proportion of counties voting for Trump between high and low unemployment rate counties is very different, right? I can really reject that they're the same. I can reject this value of 0 strongly, okay? But generally, we kind of use those three benchmarks, 90, 95, 99%, right? I don't know, I have some other ones here. You know, we could look at high income, high proportion white. They're all 0, right? When we get really large data sets, remember what's starting to happen to our distribution. So if I had a data set, and let's say I saw the same sample difference, okay? If I see the same sample difference, when I'm calculating my test statistic, and it doesn't matter, so I've got my difference, assumed true difference, even though it's 0, and I said the standard deviation of that difference. Behind the scenes of every standard deviation, or once we get to regression, we'll start calling this the standard error. Behind the scenes of this is always going to be some function over a sample size. And generally it's over a sample size -1. But notice if I found the same difference and the sample size was 30, how would I find the p-value? I turn it into my test statistic, find the area more extreme than it, and then multiply it by 2 to get my total p-value. What happens as that sample size is getting larger? Even if I find the exact same sample difference and I'm using the same hypothesis test, what's going to happen? That standard deviation is going to get, and sorry, I should have, it's here. So if the denominator is getting larger, what's happening to this fraction? it's getting smaller. If this fraction gets smaller, what's happening to my test statistic? It's getting larger, right? Dividing by a smaller value, the new so my test, anytime, even if I found the same sample evidence, but I found it from a larger sample, what's happening to my test statistic? It's getting larger. Because I can think about it this way. Right? I've got a tighter distribution. So seeing that, same sample evidence, but now I've got a larger sample size, my test statistic is going to be somewhere out here. Now, what is the area to the right of it? Smaller. So seeing a larger test statistic, what's happening then to my p-value? My test statistic is larger. My p-value is getting smaller. My p-value is smaller. Am I more or less likely to reject the null? More likely, right? So even seeing the same sample evidence, if I'm taking larger samples, it's going to be more likely I can reject the null. So if I've got sample sizes of 3,000, right? I mean, that's pretty large. What's going to be true about my p-values? They're likely going to be very small. Sure enough, when I'm testing for differences between these groups, I'm ending up with p-values of 0, right? So larger data sets are always preferred, right? In the sense of it's much easier for me to find statistical differences between groups, okay? Any questions on that idea? Here with this, okay? Where are we at in time? So we get out of here at what, 35? Oh, what do I want to do? We could do another one here. So I tried to find one. So this is just going to prove to you the point. If I've got really large data sets, I can probably find differences in things that maybe aren't really that related. It's just because it's a really large data set. If I'm assuming the difference is 0, it's likely the difference is never actually 0, even if it's really small. So I was like, what's something that should not maybe matter? And I thought maybe commute time was a variable in this data set. And so I was like, okay, I'll create a new variable that's, do they have a long commute or not? And I looked at the average commute time and it was like 23 minutes. I then ran this test to see what's the difference in the votes for Trump between long commute counties and not. I ran this. Okay. Well, I'm starting to get p-values. It's something I didn't think would be, I mean, why the hell? I mean, guess maybe there's like, you live in the city, maybe your commute is longer, but I don't know. If you're rural, you're driving further, but there's less traffic. And then if you're in Indianapolis, to go 5 miles can take me forever, right? So it shouldn't really be correlated with any of these things that are like rural or inner city. And sure enough, if I'm looking at counties that have long commutes versus those that don't, can I say that there's actually a statistical difference in the proportion that was voting for Trump? Well, the p-value is 0.22, not at any of my conventional levels, right? 90, 95, 99%. P-value is going to be less than my alpha at all three of those values. And so there is still like a slight difference out to the third decimal. Like I will find a difference, right? I mean, it's unlikely from data I'll find the exact same values. There is still a difference in these groups, but it's so small, even given that I've got a really large data set, I can't say that the proportion of counties that have long versus short commutes are voting any differently for Trump or Republican candidate, however you want to think about it. It took me a while, by the way. I tried like every variable in this data set to find something that didn't have a difference because it is larger, and this was one of the only ones that did. So I was glad. Yeah, there will be evidence sometimes we don't see differences, right? And this is one example. Okay. Any questions on this before we go in here? All right, so that kind of finishes out thinking about how we could do hypothesis testing, looking at differences between two groups. You might have to create these new dummy or indicator variables in order to do so, but that should give you everything you need. We're looking at this first problem set. Those last couple questions. I was just looking for the difference in alcohol consumption between Greek and non-Greek students. So it's just different variables, similar setup, right? Is the mean alcohol consumption different between these two groups? You'll have to use the p-value, thinking about, can I say it at certain levels? Same kind of idea, looking at the difference in GPAs for students that have above or below the average ACT score. So it's a very similar, like everything that we just worked through in that do file is a really good roadmap for how to answer these last two questions. Okay. Questions over anything there? Yeah.
I don't know if you had said this, but do file, do you want us to use for the assignment, just the review of statistics one, or?
So, I mean, technically, you don't need to use any of them in terms of like, you're creating your own,
Okay.
right? But in terms of like a good, so I try to give you do files that'll be helpful to answer questions in the problem set.
Okay.
So this one's a little bit easier because I believe everything you need to answer that first problem set is in that review of statistics do file. Moving forward, we might have two do files we use in class for problem set 2 that will, like the first 5 questions we covered in this week's do file, the next 5 because usually these problem sets go over like more than just 1 week. It's usually over multiple weeks. It's just the first 2 weeks, I kind of combine them all into one do file since we were kind of just getting going. Does that make sense?
But we're making our own for this one.
Yeah, every problem set, you're creating your own do file,
Okay.
right? The do files that we use in class are just me showing you kind of the commands and what you would need to answer the types of questions that you have in those problem sets. Yep. Any other questions here? Did I answer your question that you asked me before class?
Nah.
What was it? Because it was a good one.
Well, like, because you record all the lectures.
Oh, yes. It wasn't related to state at all. Okay.
I found it.
Okay, it's good for me to mention that. So I wanted to add, that's why I asked. Are any other questions? Got a couple more things I want to mention before we get out of here today. So, well, this is all regression stuff. We'll save this in-class quiz. I guess you're kind of getting a little bit of a cheat. You know that I'll be using it Thursday. But we'll have an in-class quiz. And we'll kind of extend a lot of what we talked about today to linear regression. I'll still do a little bit of a review of the theoretical side of it, but I'll also kind of start to show you more how it's applied in Stata. I would kind of before that class. So a couple of minutes left here. I just want to, really what we're doing with linear regression, if we're looking at kind of scatter plots at its core, and trying to figure out, is there a relationship between two variables? Now, we want to know, is there no relationship? It would be like a horizontal line, positive relationship, upward sloping, negative relationship, downward sloping, right? We will initially not talk about nonlinear relationships. Later on this semester, we'll start to actually see how we can pick up relationships that have curvature to them. So in a lot of your econ courses, like what do you start out with? You start out with linear demand, linear supply. What do you then progress to? You actually have some curve. We're going to see how we can estimate supply and demand equations. Initially, just linear. Then we'll get to like, we know that they're not actually linear. How do we pick up the fact that there's going to be relationships that are actually concave, convex? We could even do cubics if we really wanted to. I probably won't push you quite that far this semester. I'll talk a little bit more about kind of what's behind the scenes mathematically. And while I like to focus, like we need to know what Stata is doing, I also want to focus on like how our life is made so much easier. We'll look at the theory and then we'll say, okay, how does Stata make this in practice so much easier for us, right? To where if we had to do this work by hand, it used to take people like run regressions with 4 computers, I mean, weeks, right? To do some of this work. Now it takes us literally seconds, okay? So the question I did want to make sure I revisited. So I put up so I have the link in the first week's slides and in the syllabus, but if you just search Professor Lantis, I'm the first person that pops up. If you go to playlists, we've got Fall 371. Wants to hear me talk. So I put up, and they're not in order. I tried this to do it, and I'm not YouTube savvy enough, but they pop down here at the bottom, which maybe is a good thing since they're replacement classes. But I had some classes from when I taught this last spring, which are basically covering confidence intervals and hypothesis testing. So I know we touched on it a little bit here today, kind of really like the end result of it, and really what we'll primarily be using for the remainder of the semester, focusing on the detail tests, the IP values, and then kind of these critical values. But here would be if you didn't attend class last week, or I don't know. To be honest, I don't know how so person that replaced me, I don't even really know them very well. So I don't know how well it was. But if you want a replacement of kind of how I would have taught those classes, I've got 2 replacement videos kind of up there on the YouTube playlist. And this is where I'll put today's recording, kind of every subsequent recording. They'll always be here. I had someone ask me, and I'm generally, I think, better about turning it. I think today I turned it on. I don't want it to be perfect substitutes. So I said, you'll have everything we go through, especially in Stata. Anything that I'm drawing up here, generally, you're not going to be able to see in these recordings. I think that might be a caveat in the ones that I posted up here. Some of the work I had kind of saved in there. So that worked out kind of nice. But that's where the recordings are. So again, searching Professor Landis is probably the easiest way on YouTube to get. You could, pretty quick. Good question.
Yeah, do you have any like specific resources you recommend for finding stata commands?
So anything that you need for this class should be. See if I can get back to Canvas. Should be in any of those do files, but I did put up, I think there's like a starting stata. I forget exactly what I called it. The files. One materials maybe. So I think it was useful stata commands. This just has some basic ones, kind of starting out some of the stuff that we're doing. I would, I have an assigned book for this class that is more on the theoretical side. To give you something, someone stopped by my office, actually. Stop Zoom. Why is it not?